Welcome back! In this lecture, we learned tests of association and tests of difference are the same thing. Last lecture, we saw that the general linear model, that is regression, generalizes to situations where the outcome variable, the dependent variable, is categorical. Logistic regression uses linear models to predict a binomial outcome through the clever use of natural log transformation, as we saw. We could also predict categorical outcome variables that have more than two outcome states using something called Poisson regression, which is great for rank order dependent variables or interval level dependent variables that only have a few possible options. We won't be doing that, but it is pretty common. These situations, logistic regression and Poisson regression, are examples of the generalized linear model, and we have already covered all we are going to cover of that. What we're doing now is looking at the general linear model, the equation that makes the best possible straight line through a set of points. Here it is, as we've seen it before, with only one predictor. We can add in as many more as we want, thanks to matrix algebra, and this brings us to the lesson. The general linear model, the straight line through lots of points, is the core or backbone of so many different analyses that it's only a little hyperbolic to say that everything is the same thing. Specifically, we'll start with correlation, regression, and t-tests. At their core, they are the same thing, the general linear model. Since telling is neither interesting nor convincing compared to showing, let's jump to an example. This is data from 102 undergrad intro stats students. They filled out a survey about their procrastination behaviors and some big 5 questions assessing conscientiousness. It should not be hard here to predict that the relation will be a negative correlation. As conscientiousness increases, procrastination decreases. Great. This, of course, proves nothing, since the pattern could be driven by impression management or honesty. We just want some data with a signal to play with. First, let's see an example of what you already learned in the correlation/regression lecture, that correlation and regression are the same thing. Specifically, in simple regression, the slope is just an unstandardized correlation. We get the correlation coefficient by standardizing that slope. Here we have the results of a correlation analysis. The t-score is negative 5.5743 with a p-value, a probability of obtaining the data in the world where conscientiousness and procrastination are not related, that is 0.00000021113, and a negative correlation of 0.4868946. Okay, same variables, let's run a regression. Here, we have to be explicit about what is predicting what. So, we say that we want to predict procrastination from conscientiousness. We could conceivably want to predict conscientiousness from procrastination, but let's not. We, notably, get a lot more information or output from our regression analysis. Let's zoom in on the test of whether the slope, or adding the predictor variable, adds to the predictive power of the model over and above just predicting the mean value all the time. We have a highly statistically significant p-value whose t-score is negative 5.5743 with a precise p-value, the probability of obtaining the data in the world where conscientiousness is not associated with procrastination, that is 0.000000211, and I bet the next value is 3, right? So the t-test for the slope of the regression line is the same as the t-test for the correlation coefficient. This makes sense and is just a demonstration of what we already saw in terms of how each are computed in earlier lecture. A secret bonus here is the fact that the regression output also gives us the correlation coefficient. It's just squared and referred to as multiple r squared. To make things explicit, our general linear model is the computed y-intercept and slope, which we can now use to predict any y from any x. Now, when we state our model, we typically leave out the error, and we usually write y hat to mean estimated outcome. Let's pick a realistic conscientiousness score of 4.7 out of 5 and see what the model predicts for this student's procrastination score. 30.3. Okay. It can only be a value on our regression line, so we can eyeball it to kind of check our work here. There it is. Recalling that correlation is regression with a standardized slope, i.e. a slope whose value is a standard measure of the magnitude of the linear relation of two variables, regardless of the scale or units of those variables. If we wanted our regression to more exactly be our correlation, we can use the scale function in R to center each variable at 0. The scale function essentially turns each score into its z-score. It takes the score, subtracts the mean of the scores, and divides by the standard deviation of the scores. So we have conscientiousness scores standardized and procrastination scores standardized. In practical terms, this eliminates the y-intercept, which may or may not be intuitive to you. What does the analysis give us? It gives us a slope identical to the correlation coefficient. Neat! But you probably didn't need any more convincing that the correlation and regression are the same thing. There's some things to note here. First, that this works for higher dimensional models as well, ones with more predictors. Second, that this higher dimensional case allows us to see and compare the relative additive contributions of each independent variable to the prediction of the dependent variable. And third, t-values, r-squared, and f-test results are all unit invariant, so scaling is not going to affect them. We obtained the same values for the non-scaled procrastination and conscientiousness scores as we did for the scaled ones. If we want to use the model for manual prediction, it's an easier task than we had with log regression. Since we don't need to undo any log transformations, we just need to unnormalize. Let's take the same example of a student with a 4.7 out of 5 on conscientiousness to plug in her example. To plug in her value, we would have to scale her value, or standardize it in the same way we did for all the others, using the mean and standard deviation of conscientiousness. So step 1, subtract the conscientiousness mean from her score and divide the difference by the standard deviation of conscientiousness. We get 1.69659. This is the x that we put into the equation to get our scaled predicted value, which we then promptly unscale by 1, multiplying it by the procrastination standard deviation and adding the procrastination mean. Ta-da! It's 30.3 again. Great. Let's take a look at the plot of the scaled variables, which is the same, save for the units on the axes. And there's our 4.7 student in precisely the same relative space as before. We could also cleverly note here that the mean of x predicts the mean of y. Here we are, being clever. We unscale it. And yay. Okay, let's move away from regression and its quote-unquote predictors, which are busy assuming fixed effects, and move to a test of mean difference. Let's look at t-tests. But wait, we were already looking at t-tests. The significance of our associations were determined by tests of difference. What? Oh yeah, our p-values came from t-tests. Let's break down these arrows a bit more. As described in the regression lecture, the t-test for the significance of the slope is the comparison of the model predicting with no slope, i.e. predicting the outcome variable's mean value every time, with the model predicting with the slope, i.e. adding the information from the independent variable or predictor to make a slope. In other words, as we will see, the t-test is just a comparison of two conditions of a regression analysis. Let's get into it. To show how this is done, recall that the residual standard error pointed to here by the blue arrow is actually just the standard deviation of the residuals, the amount we can typically expect to be off by or wrong in our estimates. More precisely, the sum of square differences between each actual score and its model estimate, the value we predict. Okay, Professor, let's pretend I remember that. What's the green arrow? Well, we can read from the table that it's the standard error of the regression beta, or partial slope, which is, in this simple regression case, the entire slope. What connects these is the fact that the standard error of the regression slope is just the residual standard error, how much our predictions tend to miss the actual observed y values, standardized by how much x tends to vary, in purple there. So we have how well our model is doing in blue divided by how much our predictor tends to vary in purple. We want our predictors to vary then, because look at what it's doing as a denominator in the standard error equation. As variation in x increases, standard error shrinks. So the denominator of our observed t-score is the standard error of the regression slope, which is the residual standard error divided by the sum of square deviations of that slope's x from its mean. That is what we standardize the beta estimate by to get a value that corresponds with our ideal distributions, the ones we have all the values for and that we can look up in tables. Recall this table from the correlation/regression lecture. It maps R values, correlation coefficients, to significance values through t-distributions. And because we can get t values directly from R values, we could plot them together. Let's take a look at what plotting them all together would look like. Here are t's as a function of r's when we have a sample size of 102, as in our procrastination conscientiousness example. And here are t's as a function of r's if our sample size were 30. So keeping in mind that the relations would be different for different sample sizes, with r's of the same size yielding t-scores that are larger if those r's come from samples that are larger. We now also see why/how whenever we run a t-test, we can also calculate r squared as an effect size for that t-test. We just square t and divide by t squared plus the degrees of freedom. That's right, you can get a correlation coefficient from a t-test. It's the same thing. It's all the same thing. So let's do it. Let's start with an actual t-test. Let's come at things from a different angle now. From the t-test lecture, we have the example used for the independent t-test. All Klingons, rather, are Klingons more aggressive than humans. We end up with an observed t-score here of 6.2668. The p-value is telling us the data are very unlikely in the universe where Klingons and humans are equally aggressive, and from these estimated parameters we can compute our R-square effect size, from which we learn that we are explaining or accounting for 76.6% of the variation in violence with our Klingon versus human distinction. Our test of difference is a test of association. The fact that humans and Klingons differ in aggressiveness is the same thing as the fact that being Klingon versus human is associated with aggressiveness. Tests of difference between levels of a variable, like the variable species, on some outcome variable, are the same as tests of association of the variable and that outcome variable. Imagine starting with one big column, n equals 14 in this case, of violent acts, and note that half of our observations are Klingons and half are humans. We code this as a second variable. Then, in regression language, we ask, does classifying these data by a second variable, Klingon versus human, add to our ability to predict column values? In t-test language, we ask, would we be surprised by these data if there were no group differences on the second variable, Klingon versus human? Expressing this in terms of the general linear model, we have violent acts equal beta sub naught, your y-intercept, plus beta sub 1 times species, plus some error. Okay, now, just to prove that we haven't tricked ourselves, let's run t-tests on these two different arrangements of the data. T observed still equals 6.2668. to the same level of statistical significance. But now that we have the data thusly arranged, and we've proven that no funny business has occurred, we can run a regression. The code for it here is framed in baby blue. What do our results look like when we take our difference question, are Klingons more aggressive than humans, and run a linear regression on this difference question? Well, our y-intercept is the mean number of violent acts by Klingons, and the slope is the human mean minus that Klingon mean. Let's break this down. Our independent variable is neither human nor Klingon. It's rather the variable that includes both. So let's call our independent variable or predictor species. Now, let's say species is Klingon. The model in this case predicts 15 violent acts. Okay, what about when the species is human? You guessed it, the model predicts 3 violent acts. Returning to what we were breaking down from the other direction in our conscientiousness and procrastination example, the thing being compared in the t-test is actually a slope of 0 versus a slope of -12. That is, guessing the mean of the outcome variable, here the mean of Klingons, every time, versus incorporating the information of the independent variable, here the fact that 2 different species exist. Are you not entertained? The test of difference is a test of association. Summing up thus far, everything is regression. Correlation is regression, regressions are regression, and t-tests are regression. Yet, this is also to say that everything is t-tests. Correlation is t-tests on slope versus no slope, which is just regression. Even our tests of difference are just tests of association of the grouping variable with the outcome variable. We have one trick and lots of names for it. What we pragmatically care about in all cases is how well we are doing with our model, with our description of the world, with what we're looking at. And we see from our output here that this model tends to be off by 3.5 violent acts. But it accounts for 76.6% of the error that we would have if we had just used beta sub naught, i.e. if we had no slope, i.e. if we did not take species into account, i.e. if we had just guessed the mean value of aggression, regardless of species, every time we wanted to predict the number of violent acts. One more quick DIY example before we move on to ANOVA. I found myself one term teaching the same class at both the University of Toronto and Trent University, so I gave students from U of T, coded as 0, and Trent, coded as 1, the same lectures, the same materials, and the same test, which occurred in the same week for both universities. You can choose for yourself the analytical or narrative frame that works best to help you understand an analysis of this data. The point here is that whether we're asking how much university is associated with score, whether adding university to our model reduces our prediction error, or whether there is a difference in scores between universities, we're actually making the same analysis. We're effectively asking the general linear model to do the same thing for us. Next lecture, we'll expand this out, or up. ANOVAs are just general linear models. What's more, they're just special versions of regression. If you can master regression, the general linear model and all of its application potential are yours. What's more, all of the generalized linear model applications open up to you as well. Stay tuned!